Hello. Hello. So guys, I hope you might have tried DPP of performance of IC engine, where we had discussed the combustion of the fuel. Okay. So in case there is any doubt in these questions, you can see the solutions over here. Okay. So the first question says, what is the octane number of a fuel if the fuel mixture containing 30 gram of isooctane and 5 gram of normal heptane? So a engine test is performed, and in which whatever is the fuel that is burnt, that same quantity or same proportion of the fuel which was producing the same knocking was burnt, which is a mixture of normal heptane and isooctane. Okay, so now he is asking what is the octane number of the fuel which was burned or which was tested. So we know that octane rating is defined as percentage of isooctane in a mixture of isooctane and normal heptane. Okay, so isooctane percentage can be written as mass of isooctane divided by mass of isooctane plus mass of normal heptane. Okay, so you see that this can be written as 30 divided by 30 plus 5. So this is 30 divided by 35. Okay, I think answer should come out to be 85.71. Okay, so 30 divided by 35 is 85.71. Okay, so this is what is the octane number of your fuel. Is it clear? Okay, so this is the octane number. Moving on, the next question was again very easy. It says in a Morse-key test, I think there is some camera is slightly off. Okay. So it says in a Morse-key test on a 3-cylinder 2-stroke engine, SI engine, the brake power is 10 kilowatt. So we have the brake power measured in normal condition, that is your 10 kilowatt, and the brake horsepower of individual cylinder with spark cutoff are 6 kilowatt. So when one of the cylinder is cut off, so this is your BP1. BP1 is your 6 kilowatt. BP2 is your 5.9 kilowatt and BP3 is your 5.95 kilowatt. Okay, so it says the mechanical efficiency of the engine is, so once we know these three powers, BP1, BP2, BP3. From these, what we calculate, we actually calculate indicated power in cylinder 1. So indicated power in cylinder 1 will be equal to brake power in normal condition minus your brake power in the condition when first cylinder is cut off. Okay, so 10 minus 6, that will be equal to 4.1 kilowatt. Is it clear? So the first is 4.1 kilowatt. Going on next, when we calculate indicated power of cylinder 2, that will be equal to brake power minus brake power 2, that is equal to 10 minus 5.9. So that is this is 4 kilowatt. 4.0 kilowatt, this is 4.1 kilowatt. Okay, second is indicated power in third, so third will be BP minus BP3. Okay, so that is 10 minus 5.95, so that is 4.05 kilowatt. Is it clear? So once we have calculated all the three indicated power, now we can calculate total indicated power. So I total will be equal to 4 plus 4.1 plus 4.05, that is 12.15 kilowatt. Okay, so your indicated power is 12.15, brake power is 10. So you can calculate mechanical efficiency or transmission efficiency, whatever you call it, that is 10 divided by 12.15. Okay, so what the answer will be? 10 divided by 12.15, so 10 divided by 12.15, that is 0.823. So 0.823. So mechanical efficiency is 82.3%. Okay, so we can write 82.3%. Is it clear to everyone? This was again a very easy question. So generally in case of performance of IC engine, we have very easy questions coming in all the cases. Okay, let's go to the next question. It says it is a question of your rope dynamometer. So it says a rope dynamometer is used to measure power of an IC engine. If the rope is wrapped by 2 turns on the dynamometer shaft, okay, then the power developed by engine when tension in the slack and the tight side of the rope is 50 and 500 Newton. So the tension in the tight and slack side is given. The drum radius is 0.5 meter and the engine rotates at 3000 RPM. So how does this dynamometer actually looks like? So you see that this dynamometer would be looking something like this. So this is the shaft, okay, and on this shaft there will be a rope that is attached over here. So let's say this is where the rope is fixed, and there will be this rope is wrapped by 2 turns. So 1 turn and then 2 turn, and then finally you have the other end which is over here. Okay, so when I'm writing this, so guys, you should understand that these 2 turns are wrapped over something like this. So this is your first turn, okay, and then this will be your second turn. So this is your first turn, then this is wrapped your second turn, and this is how your weight will be acting. Okay, so in this weight it is saying the tension over here is 500 Newton and the tension in this side is your 50 Newton. Okay, so let's say you can assume this is T1, you can assume this is T2. Okay, so the torque on generator will be equal to torque T1 minus T2 multiplied by radius. Okay, so T1, T2 are given, radius is given as 0.5 meter and the engine is rotating at your 3000 RPM. So R is given as 0.5. So torque can be calculated as 500 minus 50 multiplied by 0.5, that is equal to 450 multiplied by 0.5, that is 225 Newton meter. So torque is 225 Newton meter and your engine is running at 3000 RPM. Okay, so N is given as 3000. Okay, so we can calculate what is the power produced. So the power produced, brake power, will be equal to torque multiplied by omega. This will be equal to 225 multiplied by 2 pi n divided by 60. Okay, so this can be written as 225 multiplied by 2 pi multiplied by 300 divided by 60. Okay, so the answer will be equal to 225 multiplied by 2 multiplied by pi multiplied by 50. Okay, so 70.685 kilowatt. So 70.68 kilowatt. Is it clear? This will be the power that is produced by your the power that will be produced in the crankshaft. This is what is the power that is available with actually the crankshaft. Is it clear to everyone? Okay, so you can write 70 point. Answer is 70.685 kilowatt. Is it clear? Okay, so now let's go to next question. Guys, this was the easy question. The only thing that you had to do was in the class we had discussed how does a rope dynamometer works. Okay, so that we had already discussed and I told you formula how to calculate. So in the class we had discussed how does a Prony dynamometer works and how does a rope dynamometer works. Next question says, in a motoring test was performed on an engine to calculate frictional power of an engine. If the motor consumes 10 ampere of current at potential difference of 220 volt. So what he's saying is this is a motor. Okay, this is your motor and this is connected to your engine. Okay, and now when you are performing the test, you know that whatever is the power that is supplied by the motor to the engine to rotate it, the same power will be the frictional power. So this motor is drawing a current of, this is at 220 volt difference and it is drawing a current of 10 ampere. Okay, so the power that is available to the motor, power input is your 220 volt multiplied by 10. Power is equal to VI. Okay, in 11th class you might have studied power is equal to VI. So this is 2.2 kilowatt. So power that is coming into the motor is your 2.2 kilowatt. Okay, from here this is your power in. Now your motor is having an efficiency of 80%. So whatever is the power that is going out, P out. Okay, so P out will be 80% of what the power that is coming in. So P out will be 0.8 times multiplied by 2.2 kilowatt. Okay, so this will be 1.76 kilowatt. Okay, I think 22 multiplied by 8 is 1.76 kilowatt. Okay, so the answer that is given is in option number A. Okay, so this is what is very easy question. Next question was again of a brake dynamometer. That was again very interesting question. This is one of the question that could trouble your mind. Okay, very interesting, very easy, very good question. It says a brake dynamometer is used to measure power developed by engine. It measures a torque of 500 Newton meter at an engine speed of 900 RPM. Okay, the torque measured by this dynamometer is the engine speed is dropped to 600 RPM on reducing the fuel supply to 25%. Okay, so what happens is, let's say your dynamometer is measuring the power. So can I say the torque that is measured at, or the power that is measured at 900 RPM can be written as torque multiplied by omega. Okay, and the torque that is measured is 500 Newton meter. Okay, so this can be written as 500 multiplied by 2 pi n divided by 60. Okay, so you can calculate this power. This will be equal to 500 multiplied by 2 pi multiplied by 900 divided by 60. Okay, so the power that will be measured over here will be equal to, that power measured by dynamometer is equal to 500 multiplied by 2 pi multiplied by 15. Okay, so 47.123 kilowatt. Okay, so this is what is the power that is measured. Now you see that this is your brake power. P900 is your brake power at 900. That is the power measured at 900. So brake power is 47.123 kilowatt. What will be the indicated power at 900? So that will be brake power at 900 plus frictional power. Okay, so what is the frictional power? So if you see, he has given you the frictional power of engine is 2 kilowatt. Is it clear? So you can say that the indicated power of this engine is 47.123 plus 2, that is 45.123 kilowatt. This is your indicated power at 900. Okay, now what he's saying what will be the power, or how much is the torque that is measured when the RPM drops to 600. He is saying when the RPM is dropping, he has cut off the fuel supply to 25%. If he cuts off the fuel supply to 25%, what will happen? Whatever is the energy that you are supplying to the cycle QS, that will reduce. And if QS is reducing, your indicated power will reduce. So you see that at indicated power at 600 will be equal to 0.75 times indicated power of 900. 25% power will be reduced. Okay, so what will be the power that is produced by your engine? It will be 35.342 kilowatt. Indicated power at 600. And based on this indicated power, what will be the brake power at 600? So brake power at 600 will be equal to indicated power minus 2 kilowatt. So 33.342. 33.342 kilowatt is your brake power, and this will be equal to torque at 600 multiplied by omega. Okay, so torque will be equal to 33342 divided by 2 pi multiplied by 600 divided by 60. Understanding? Okay, so divided by 2 pi divided by 10. Okay, so the torque measured, oh, I'm sorry. So 33342 divided by 2 divided by pi divided by 10. So 530.65. Is it clear? So the torque that will be measured by your dynamometer is more. Is it clear? 530.65 Newton meter. Is it clear? Okay. So 535.65 Newton meter. So this was an excellent question, very good question. One of like mind twisting your question. Okay. So in this DPP, this was one of the best questions. Okay. Again, there is a question of combustion. This question was again very easy question, not very difficult. So it says 44 kg of C3H8, that is propane, is burnt with air, that is molecular weight 29, to produce 44 kg of CO2 and remaining CO. What is the approximate amount of air used in the combustion? So he is saying that CO is produced, carbon monoxide is produced. So if you are burning C3H8 and your carbon monoxide is produced, then can we say carbon monoxide is produced, then can we say this is your incomplete combustion? Okay, so this will be leading to CO2 plus CO plus your H2O. Okay, so now he is saying you are burning 44 kg of C3H8. So what is 44 kg of C3H8? 44 kg, that means you have the mass of this is C3H8, you have a molecular mass of 44. This also has molecular mass of 44. This has a molecular mass of 8 is 16 plus 12, that is 28. Okay, so now it says 44 kg, that means the molecular mass is 44 gram. So that means there should be 1 kilomole of C3H8 that is burnt. When one kilomole is burnt, there is 1 kilomole of your CO2 produced. Okay, so that means if this is your 1 kilomole, then this is your 1 kilomole that is produced. So whatever we are taking, we are going to balance this equation in terms of kilomoles. Okay, so we have 1 kilomole here, 1 kilomole here. Now remaining will be CO2, CO. So we will balance it first. So we have C3H8. So first carbon will be balanced. So you see that one carbon, one C3, that means 3 atoms of carbon, 1 carbon over here. So there will be 2 kilomoles of CO produced. So now the carbon is balanced. Now hydrogen is 8 over here. So there will be 4 over here. Okay, so now we can go for balancing of oxygen. There are 2 plus 2, 4 plus 4, 8. So you have 8 atoms. So there will be 4 kilomoles of oxygen will be used. Okay, so you see that for 1 kilomole, the air that is used is 4 kilomole. Okay, and when you have 4 kilomole of air, mass of air will be equal to 4 multiplied by 29 kg. Why we are writing kg? Because air has a molecular mass of 29 gram per mole or 29 kg per kilomole. So the amount of air will be equal to 116 kg. Okay, so you see the approximate amount of air used in the combustion will be air has 1 mole. Okay, so this is your air. We are not writing this is not correct. There will not be 4 kilomole. So we are using 4 kilomoles of oxygen. Okay, so 1 mole or 1 mole of air, this has 79% oxygen, 79% nitrogen and 21% oxygen. Okay, so 1 mole of air has 0.21 moles of O2 and 0.79 moles of N2. Okay, so per 0.21 moles, you have how many moles of air? So if you have 1 mole of air, 1 mole of O2, then the mole of air would be, if it is 1, then the mole of air will be 1 divided by 0.21, that is equal to 4 point something Okay, so 1 divided by 0.21, that is 4.76 moles. Okay, so 4.76 moles of air will be there per kg per 1 mole of oxygen. So you have air here. The mole of air that is used is something in which you have 4 moles or 4 kilomoles of oxygen. So you have 4 kilomoles of oxygen, that means 4 multiplied by 4.46 kilomole of air. Understanding? Yes or no? Is it clear? So this is what is the mole of kilomole of air that will be used. So if you have 4.46 multiplied by 4, so the amount of air will be used is, mass of air will be equal to 4.76 multiplied by 4 multiplied by 29. So 116 multiplied by 4.79. So this will be 552 kg. Okay. So guys, we made a small mistake over here. So oxygen, if you see in one kilomole or 1 mole of air, you have only 21% oxygen. That means 0.21 moles of oxygen. But here we are having 4 moles of oxygen. So for 0.21 moles of oxygen, you have moles of air as 1. For 4 moles of oxygen, you will have 1 divided by 0.21 multiplied by 4. That is 4 multiplied by 4.76 moles of air. Understood? So the amount of air used will be equal to 550 kg. Roughly it is saying. Is it clear to everyone? Yes or no? Is it clear? Okay. So this was again an excellent question. Very good question. Okay. So now let's go to the next question. Again, this is of the combustion. So it says a fuel containing 47% carbon, 42% hydrogen, 10% oxygen and 2% sulfur by weight is burnt in presence of air. If the mass of fuel is 1 kg, then the mass of air required so that sulfur produce SO2 is. Okay. So this says 47% carbon. So you have carbon plus you have hydrogen plus you have oxygen plus you have sulfur, and then you are supplying O2 plus 79 by 21 nitrogen, and when this is burning completely, it is producing CO2 plus H2O plus SO2. Okay. So now you see that he is giving you 1 kg of the fuel. So if he is giving 1 kg of the fuel, okay, if he is giving 1 kg of the fuel, then what will be the amount of CO or C, carbon? He is saying 47% carbon, 42% hydrogen. Okay. So when we say 47% carbon, that means 0.47 kg of carbon. Okay. So 0.47 kg of carbon, this would lead to how many moles of carbon? So we will divide 0.47 divided by 12. Okay, so 0.47 divided by 12, that is 0.47 divided by 12, that is 39.16 moles of carbon. Okay, 39.16 moles of carbon. This is 0.47 kg of carbon divided by 12 gram. So that means we 470 divided by 12. 470 divided by 12 is 39.166. So this is the number of moles of carbon. Okay. Then you see hydrogen. So 1 kg of fuel will have 0.42 kg hydrogen. Okay. So what is hydrogen? This is 42%. So 0.42 kg. Now the molecular mass of your hydrogen H2, if I take, you can write it like this. Okay. So molecular mass of hydrogen is 2. If it is 2, then the number of moles will be equal to 42 divided by 2. Okay, or 420 divided by 2, that is 210 moles. Okay, so 210 moles of hydrogen H2. Okay, then you have sulfur. So your sulfur is given as 2%. Okay, 2% sulfur. So when sulfur is given as 2%, so 0.02 kg of sulfur. So what is the atomic weight of sulfur. Atomic mass of sulfur is 16. Atomic number of sulfur is 16. Atomic mass is 32. Okay. So molecular mass of sulfur is 32. Okay. So if it is 32, you can say 0.2, or you can say 20 gram, 20 divided by 32 moles of sulfur. Okay. So 20 divided by 32, that is 0.625 moles. Okay, 0.625 moles of sulfur. Is it clear? And he says 10% of oxygen. So you can say 0.1 kg of O2. So if you have 0.1 kg of O2, the molecular mass of O2 is 32. Okay, so you can say 100 gram divided by 32, that is 3.125 moles of oxygen. Okay, so you see everywhere you can write 39.16. Here you have 210, and then here you have 3.125, and sulfur is your 0.0625. So plus 0.0625. Okay. So now corresponding to all these moles, you can calculate what will be the amount of oxygen required. Okay. So how much of oxygen will be required? So if you have 39.16, you have 39.16 carbon. You have 39.16 moles of carbon. Okay. So this will be converted into 39.16 moles of CO2. Okay. So from here you will require 39.16 O2. Okay, 39.16 moles of O2. Why? Because this is 1 mole. 1 mole of carbon will use 1 mole of O2. So 39.16 moles of O2. Then you have 200 moles of hydrogen. That would combine to produce 210 moles of H2O. So if you see H2O, hydrogen is using 2 hydrogen is using 1 oxygen. So you can write 210 divided by 2, that is 105 moles of O2. We are writing moles of O2. Why? Because if you see over here, we will be writing the moles of O2. So we will multiply the number that is coming over here. Understanding? Okay, so you have written O2, then you have sulfur. So sulfur is 0.625 sulfur. That leads to SO2. Okay, so 0.625 SO2 will be produced. That will lead to 0.625 moles of O2. Okay, so the total requirement of the moles in reaction will be equal to this 39.16. Okay, 39.16 plus 105 plus 0.625. Okay, this is 0.625. Okay, so this is the total requirement, that is 144.785. So 144.785 moles of O2. So this is the requirement. But you see that your fuel already has 10% of oxygen, and that 10% of oxygen already has 3.125 moles. So minus of 3.125 moles of O2. So you see that once you have 3.125 moles of O2, so now you can minus 3.125. So the total requirement is 141.66 moles of O2. Okay, so you have 141.66. So you can put 141.66 plus 141.66 O2. That will lead to CO2, H2O, everything. Okay, so this is 39.16. Then H2O is 210. Okay, and finally 0.625. Is it clear? So you see that the oxygen that is present over here, that will be used along with it. Is it clear? So the total requirement was 144, but out of those 144, 3.15 is already available. So the moles of air, extra air that is required is 141.66. And if it is 141.66 moles of air, so 141.66 moles of O2. Okay, this will lead to how many moles of air? So multiplied by 4.76. Okay, So 141.66 multiplied by 4.76 of air. These are the moles of air. Why we are writing these are the moles of air? Because the number of moles, you see that the air is 0.21 for 1 k, or for 1 mole of air. Okay, 1 mole of air contains 0.21 mole of oxygen and 0.79 mole of nitrogen. Is it clear? Okay, so you see, if it is having 0.21 moles, so for 1 mole of oxygen you will have 4.76 moles of air. So 4.76 moles of air, that will be equal to 1 mole of O2, okay, and 79/21 mole of nitrogen. Okay, and this is what is we are taking in the reaction. So when you are taking in the reaction, you are basically taking in 4.76 moles of your air. Okay, so 1 divided by 0.21 is your 4.21 is 4.76. Understood? So now once you have 4.76 multiplied by the moles of air required will be 141.66 multiplied by 141.66 multiplied by 4.76. So total moles of air, okay, so total moles of air will be equal to 141.66 multiplied by 4.76. Understood? Yes or no? So this is 674.57 moles of air. Okay, but in the question he is asking what is the mass of air required. Okay, so mass of air required is 674 moles. So mass of air will be equal to 674.57 multiplied by 0.029. So one mole of air is weighing 29 grams. Okay, so when I multiplied by 0.029, we will have 19.56. So 19.56 kg air is required. Okay, so the answer will be 19.56. Understood? Yes. So guys, this was again an excellent question, very good question, though it is very easy. So what you have to do is, once you are given a fuel, so you are given a fuel of 1 kg. If the mass of fuel is 1 kg, so first you have to calculate how many moles will be there corresponding to that 1 kg. So when you calculate those moles, first you have to see that if you have 1 kg of fuel, then it will be 0.47 kg of carbon, and that would lead to 39.16 moles of carbon. Again 210 moles of hydrogen, so many moles of oxygen, and so many moles of sulfur. Now you can put them in the equation. When you put them in the equation, now you can balance the equation and you can see what is the requirement of your air. So based on that requirement multiplied by 4.76 will become the number of air. Okay, and once that is calculated, you can multiply it with the molecular mass of the air, that is 29 gram per mole, to calculate what is the mass of air required. Is it clear to everyone? Is it clear to everyone? Yes. Okay. So now again the next question, that is easy. It says 1 kg of fuel consisting of a mixture of 50% methane and 50% hydrogen by volume. Okay. So you have 1 kg and 1 kg. Okay. Both are having 50% each. Is it clear? By volume is burnt in presence of oxygen. The amount of oxygen required for complete combustion in kg is. Now again, this question, if you see, when you have methane, what is methane? So CH4 plus your hydrogen. This is what is your composition. So 50% of your both the constituent are there. So you see, when this is 50%, that means this will be having 1 mole. Okay, if it has 1 mole, then this is also has 1 mole. Okay, both are having 1 mole. If both are having 1 mole, the weight of this is 16 gram and weight of this is your 2 gram. Is it clear? wait a second. Okay, so 2 gram. Okay, so now if you see, if this is 16 gram and this is 2 gram, what is the total weight of this 1 mole? You see that the total weight is 18 gram only. Okay, so now if you see in 18 gram, you have 16 gram of methane and 2 gram of hydrogen. If they are 50-50% by volume, so their volume is 50-50%, but their mass is significantly different. This is 16 gram and this is 2 gram. So if I have 1 kg of fuel, then how many moles of methane and how many moles of hydrogen I have? I can multiply 1 kg divided by 18. So that means, or 1000 gram divided by 18. So that is equal to 55.55 moles of mixture, moles of CH4 plus H2. So 1 CH4 plus H2, that means 1 mole, both of them are having 1 mole, that weighs 18 gram. So if you have to weigh 1000 grams, he is casing 1 kg of the fuel. So if 1 kg of the fuel is there, that means it should have 55.5 moles of methane and 55.5 moles of hydrogen. Understanding? So 1000 divided by 18 is, I think, 55.5. Yes, 55.55. Okay. So 55.55. So if you have 55.55, so you can see that 55.5 of CH4 plus 55.5 of your hydrogen. Okay. Now both of them are burning. When both of them are burning in oxygen plus 79/21 nitrogen. Okay. So they are burning in air. By volume is burnt in presence of oxygen, the amount of oxygen required for complete combustion. So they are not burning in air. So it is burning only in oxygen. Okay. So when they will be burning in oxygen, they will be producing CO2 plus your H2O. Okay. So when one carbon is burning, it will produce 1 CO2. Okay. And when hydrogen is burning, you see that the equation that will be balanced is your CH4 plus H2. When it will be reacting with plus of your O2, that leads to CH4, or that leads to CO2 plus H2O. Okay. So you see that carbon is only 1, so this will be 1 carbon. But your hydrogen over here, there are 4 hydrogen over here and 2 hydrogen over here. So total 6 hydrogen are there. So if 6 hydrogen are there, then 3 H2O will be formed. Okay. And if 3 H2O is formed, the amount of oxygen required will be 2 plus 6, that is 8. So the total number of moles will be 4. Okay. So you see that the number of moles of oxygen required will be equal to 55.4 multiplied by 4. So every mole of CH4 and every mole of hydrogen requires 4 mole of oxygen. So 55.5 will require 55.5 multiplied by 4 moles of oxygen, and that would lead to 55.5 and 166.5 moles of H2O, or 6 moles. That means 55.5 multiplied by 6. Okay. So 333 moles of H2O. Is it clear? Oh, my mistake. These are 4, these are 2, that is 6. So this will lead to 3 H2O, yeah. 3 H2O. Okay. And if it is 3 H2O, then this will not be 4 O2. So you have 2 plus 3, 5. So 5 by 2 O2. Okay. So it will be 55.5 multiplied by 5 by 2. Sorry. Okay. So CH4 is 4 plus 2, 6. If it is 6, then that will be 3H2O. If it is 3H2O, then 3 multiplied by, or 3 plus 2 is 5, 5 by 2. 5 by 2 multiplied by 55.5. Okay. So now you see that this much number of moles of oxygen are required. So what is the number of moles of oxygen? So moles of oxygen are, so 55.5 multiplied by 5 by 2 moles of O2 are required. Okay, so how many moles of O2 are there? So 55.5 multiplied by 5 divided by 2, that is 138.8. 138.8 moles, and 138.8 when multiplied with the molecular mass of oxygen, that is 32 gram. So 32 per gram, so that will be 4.444 kg. 4.444 kg oxygen. Is it clear? Yes or no? Yes or no? Is it clear to everyone? Understood how we did it? So guys, whenever the equation comes, you have to always balance the equation in terms of your moles first. Okay, so to balance the equation in moles first, what you have to calculate? You have to calculate what are the number of moles that are present in 1 kg of fuel. So if I give you that you have 55.5 moles of methane and 55.5 moles of hydrogen in one mixture, what is the total weight? You will directly calculate 55.5 multiplied by 16 plus 55.5 multiplied by 2. That will be your 1 kg. You will directly calculate. And in that 1 kg, you see by volume 55 by volume 55 by volume. That means these are the volumes. Equal volumes occupy, or equal number of moles occupy equal volume. Okay. So this is 55 moles. This is again 55 moles. That means 50% of the mole, 50% of the mole. Okay. 50%, 50% moles and your volume. Is it clear? So, but mass is different. So you see that now you have to balance on the moles. Once you have balanced on the moles, you see the equation would look something like this. Equation always have to be balanced on the number of moles. Is it clear? Is it clear? You should not have written that half kg of CH4 and half kg of methane. Half kg of CH4 would lead to lesser number of moles. Okay, so half kg divided by 16, that will probably come out around 33 moles. Okay, so 33 moles you write over here, but here the number of hydrogen that is coming out will be equal to very high. It will be 250 moles. Okay, so question will become wrong. Understood? Okay. Again, let's go to next question, that is of Williams line. It says the Williams line measured for a 4-stroke 4-cylinder is expressed as, so this is fuel consumed is 0.4 plus 0.1 times brake power. Okay, so when the fuel consumed is 0.04 plus 0.10 times brake power, so m dot f is 0.4 plus 0.1 multiplied by brake power, where FC is the rate of the fuel consumption in milligram per second and BP is the brake power in kilowatt. If the engine consumes 1 milligram per second of the fuel, then the indicated thermal efficiency is, take calorific value of the fuel as 40 megajoule. So indicated, he is asking you indicated thermal efficiency. Okay, so he is asking you indicated thermal efficiency, so we have to calculate indicated power. Okay, he is saying m dot f is your 1 milligram per second. So this is your 1, that will be equal to 0.4 plus 0.1 multiplied by brake power. So from here you can see that the brake power will come out to be 6 kilowatt. So brake power is your 6 kilowatt. Is it clear? 1 is equal to 0.4 plus 0.1 multiplied by brake power. This will go on this side, this will become 0.6. 0.6 divided by 0.1 is 6. So brake power measured in this condition is your 6 kilowatt. What is the frictional power? So to calculate the frictional power, the Williams line test that m dot f is equal to 0. When m dot f is equal to 0, that means 0.4 plus 0.1 multiplied by brake power. So brake power will be equal to minus 4 kilowatt, and this is what is your frictional power. So frictional power is your 4 kilowatt. Okay, so if frictional power is your 4 kilowatt, so I can write brake power minus 4 kilowatt. This is equal to minus of frictional power. Okay, so this minus, you guys don't confuse it, because we know that the negative brake power is your frictional power. Okay, so frictional power is 4 kilowatt. From here you can say that indicated power will be equal to brake power plus frictional power, that is equal to 6 plus 4, that is equal to 10 kilowatt. So brake total indicated power is your 10 kilowatt. Now once your 10 kilowatt is given, he says, if you see over here, he says you have 1 milligram per second of the fuel is burning and calorific value is your 40 megajoule per kg. So what is the heat supplied? The heat supplied is 1 milligram per second. Okay, so 1 milligram is 10 raised to power minus 6 kg per second. 1 milligram is 10 raised to power minus 3 gram. That is 10 raised to power minus 3 multiplied by 10 raised to power minus 3 kg per second. Okay, so 10 raised to power minus 6 multiplied by 40 megajoule. So 40 multiplied by 10 raised to power 6. Is it clear? So this will be your power, 40 megajoule per kg. Okay, so 40 megajoule per kg. So this will come out to be 40 this is coming out to be there is one, I think instead of milligram this should be gram. Okay, so 1 gram per second is 10 raised to power minus 3 kg per second multiplied by 40 into 10 raised to power 6 or 40,000 kilowatt. Okay, so this will leave away. So guys, this is not 1 milligram per second, it should be 1 gram per second. Okay, it should be 1 gram per second. Slight change over here. So this is 1 gram per second. Okay, again this should be gram per second. Okay, where fuel consumed is the rate of fuel consumption in gram per second and brake power is in kilowatt. Okay, so if engine is consuming 1 gram of fuel per second, so when it is 1 gram of per second, it will be equal to 10 raised to power minus 3 kg. So 10 raised to power minus 3 kg per second multiplied by 40 into 10 raised to power 3 kilowatt. So I can write 40,000 kilojoule per 40,000 kilojoule per kg. So 40,000 kilojoule per kg multiplied by kg per second. So this will become 40 kilojoule per second or 40 kilowatt. Okay, so heat supplied is your 40 kilowatt. So efficiency of the cycle could be written as the work developed or indicated power divided by the heat supplied, that is equal to 10 divided by 40, that is equal to 25%. Understanding? So the efficiency will be equal to 25%. This was an easy question. The only thing is slight I will get it corrected in the DPP. Okay, so this is 1 gram per second only. Okay, moving on to the last question, guys. Last question was again not very difficult question. It says during trials of a 4-stroke single cylinder engine, so the load on the dynamometer is found to be 20 kg at a radius of 50 centimeters. So you see, this is your Prony type dynamometer. He is giving you load and he is giving you the radius. Okay, the speed of the rotation is 3000 rpm. The bore and stroke are 20 centimeter and 30 centimeter. The fuel is supplied at a rate of 0.15 kg per minute. The calorific value of fuel may be taken as 43 megajoule per kg. After some time, the fuel supply is cut off and engine is rotated with motor, which requires 5 kilowatt to maintain the same speed of the rotation. That means the frictional power is given as 5 kilowatt. He is saying, based on the above data, which of the following options are correct? So mechanical efficiency is 86%. So he has given you frictional power, but we have to calculate what is the brake power, and once you calculate brake power, you have to calculate indicated power. So to calculate brake power, he has given 20 kg load at 50 centimeter radius and your rotation is 3000 rpm. So first we can calculate what is the brake power. So brake power will be equal to torque multiplied by omega, and torque is equal to the load. Load is your 20 kg, so 20 multiplied by 9.81. So this is your weight W multiplied by the radius is your 0.5. The lever that is given as 50 centimeter. Okay, 50 centimeter. So for a Prony type dynamometer, we have told you that this is your weight W and this is your length. That will become the torque multiplied by omega, that is 2 pi n divided by 60. So n is your 3000 rpm. Okay, so from here you can calculate what is the brake power of this engine is. Okay, so the brake power of this engine will be equal to torque, that is equal to 20 multiplied by 9.81 multiplied by 0.5. So 98.1 Newton meter multiplied by 2 multiplied by pi multiplied by 50. So 30.819 kilowatt. So brake power is coming out to be 30.819 kilowatt. Your frictional power is already given, that is equal to 5 kilowatt. So from here you can calculate mechanical efficiency. So mechanical efficiency will be equal to 3.819 divided by 35.819. Okay, so divided by 35.819. So this is 0.86 or 86%, 0.86. So you see that he is saying the mechanical efficiency is 86%. This is correct answer. Okay, so the first calculation is done. Second, he is saying the brake specific fuel consumption is 0.15. So how do we calculate brake specific fuel consumption? So what is brake specific fuel consumption? Brake specific fuel consumption is, we have already written 3600 multiplied by m dot f divided by your brake power, where m dot f is in per second and brake power is in kilowatt. Okay, this is your kg per second, this is in, it should be in your kilowatt. Okay, and based on that we will calculate kg per kilowatt hour. This is your kg per kilowatt hour. Okay, so he has given you what is the fuel consumed. So he is saying the fuel supplied is at a rate of 0.15 kg per minute. Okay, so 0.15 kg per minute. So if it is 0.15, so you can write 0.15 divided by 60 multiplied by 3600 divided by the brake power. Brake power is your 30.819. So it should be put in like 30.819 only, 30.819. Okay, so this will be your answer. So you can calculate 0.15 multiplied by 3600 divide by 60 divided by 30.1819. Okay, so this is coming out to be 0.29 kg per kilowatt hour. Okay, so you see that the second option which is given as 0.29 kg per kilowatt hour, that is correct. Is it clear to you? So guys, if you see in this question, he has given you lot of extra data. He has given you the calorific value, that is 46 megajoule. He has given you the bore, that is 20 centimeter, stroke, that is 30 centimeter. So you don't require all these data. It might happen that to make the question look very lengthy, he can give you question like this. Generally, this happens in GATE exam. Okay, so once you see this type of question, if it is very lengthy, you should not be scared. Is it clear? Okay, so I hope you might have got answer to this question. This was very easy question. The only thing is you should have understood what you have to calculate. So you have to calculate the brake power first, then you calculate mechanical efficiency, and then you have to calculate brake specific fuel consumption. Is it clear to everyone? So guys, I hope you might have found these questions to be very easy or very interesting. 2 or 3 questions were really good questions. So you might have got some good grip on the subject. Okay. So that's all in this topic and in this subject. Thank you so much.